Hey everyone, welcome back. As an electrical engineering professor, I see it all the time. Students really struggle to connect the theoretical math we write on the chalkboard to the tangible, actual circuits and systems that we're building in the lab. So this explainer is designed specifically for you, the graduate students tackling advanced engineering mathematics. Today, we're going to completely bridge that gap between physical reality and pure mathematics. We're going to do this by exploring how we use separable ordinary differential equations, or ODEs, to solve actual real-world engineering problems. Whether you're modeling voltage drops, crazy chemical reactions, or fluid dynamics, this right here is the foundational tool you literally cannot live without. So, let's dive right in. All right, here's our roadmap for this session. We'll cover the art of mathematical modeling, solving separable differential equations, exponential growth and decay, Newton's law of cooling, modeling complex mixing problems, and wrap up with ODEs and broader engineering applications. Let's get to it.
Starting off with Section 1, the art of mathematical modeling.
In engineering, the phenomena we observe every day, whether that's the velocity of a falling object, the flow of electric current through a circuit, or the decay of a radioactive substance, they are entirely dynamic. They're constantly changing. And because they're changing, they are perfectly described by an ordinary differential equation, or an ODE. Simply put, an ODE is just an equation that relies on the derivative of a single independent variable, which is usually time, to capture that exact rate of change.
I absolutely love this quote from Dr. Trefer-Bassett. He says, "The rate of change of a quantity is easier to say something about than the quantity itself." Think about that for a second. If I hand you a piping hot cup of coffee, you probably don't immediately know the mathematical formula for its exact temperature at, say, minute 37. But basic physics easily gives us the rules for how fast that temperature is dropping at any given second. We just model the change, and the math automatically reveals the final destination. It's brilliant.
So how do we actually put this into practice? Well, we lean on Erwin Kreyszig's classic three-step modeling process. Whenever you tackle a tough problem in the lab, you've got to rely on this framework. Step 1. Formulate your equations based on the physical principles. Basically, set up the rules of your system. Step 2. Solve the math. And yeah, you can totally use software for the heavy numeric lifting here. But step 3, this is the absolutely crucial part for us as engineers. You have to interpret the physical result. You take those numbers and translate them back into a physical, actionable recommendation. Like, is this bridge actually safe to drive on? Or is this drug dosage going to be effective?
Moving right along to Section 2, solving separable differential equations.
A lot of the practical ODEs we encounter can actually be manipulated into a really convenient, super elegant format. By just doing some pure algebra, we can group all of our dependent y variables on one side of the equation and all of our independent x or t variables on the exact opposite side. We end up with g of y dy equals f of x dx. And once they're neatly separated like that, you just integrate both sides independently to find your general solution. It is a massive time saver and an incredibly powerful technique.
Which brings us to Section 3, exponential growth and decay.
Notice how the exact same underlying mathematical framework yields radically different realities just based on a single constant, k. A positive k models Malthus's law for growth, which represents the explosive, unbounded expansion of a population. But flip that sign to a negative k, and suddenly you're modeling radioactive decay. And it gets even cooler. If we tweak our separable ODE slightly, say y prime equals negative 2xy, like we see mapped out in example 3 of our text, well, integrating that involves an x squared term, which gives us figure 10, the famous bell-shaped curve, y equals e to the negative x squared. That particular solution is literally the backbone of statistical modeling in our labs. So one fundamental mathematical concept gives us incredibly diverse physical worlds.
Now, when we're dealing with that negative k in exponential decay scenarios like the radiocarbon dating they use to figure out how old ancient artifacts are, you're going to see this specific value all the time, 0.693. Because of how the natural logarithm works, the half-life of any first-order reaction is roughly equal to 0.693 divided by your rate constant. And what's really wild about this is that for first-order reactions, this half-life is completely independent of your starting amount. It takes the exact same amount of time for a massive 100-gram sample to decay down to 50 grams as it takes a tiny 1-gram sample to decay to half a gram. Mind-blowing, right? All right, on to Section 4, Newton's law of cooling. Let's see how this builds on what we just talked about. Say you're evaluating the temperature of an office building in the dead of winter. The rate that the temperature drops isn't just based on the building's internal heat. No, the change in temperature over time is actually proportional to the difference between the inside temperature, which is capital T, and the ambient outside temperature, T sub A. Solving this separable ODE gives us the particular solution for temperature over time, exactly what we see plotted out in Figure 12 for example 6. Think about it. If it's super hot inside and freezing outside, the cooling is going to be incredibly rapid. But as the building's temp drops closer to the outside temp, that difference shrinks and the cooling rate drastically slows down. It is a perfect textbook example of a separable ODE in action.
Next up, Section 5, Modeling Complex Mixing Problems.
Before we crunch any numbers, we absolutely have to perform Step 1 of Kreyszig's framework, setting up the model based on strict physical constraints. Let's look at the mixing problem from example 5, illustrated in Figure 11. Picture a massive industrial tank holding an initial volume of 1,000 gallons of water with 100 pounds of salt already dissolved in it. Now we have a brine mixture pumping in at 10 gallons per minute, and every gallon carries 5 pounds of salt. At the exact same time, the perfectly stirred mixture, assuming your lab partner actually remembered to turn on the agitator, is draining out at that exact same rate of 10 gallons per minute. These rigid physical boundaries tell us something super important. The total volume of liquid in the tank stays perfectly locked at 1,000 gallons, but the salt concentration? That's going to change dynamically as time goes on.
Okay, so we formulate the rate of change of the salt, Ry prime. It's simply the rate of salt coming in minus the rate of salt coming out. 10 gallons times 5 pounds means 50 pounds are entering per minute, and the salt leaving is 10 gallons out of the 1,000 total, so that's 0.01 times y. This gives us our separable ODE, y prime equals 50 minus 0.01 y. You separate, you integrate, and boom, you arrive at your particular solution. But here is the real aha moment. Why does our salt curve eventually just flatten out at exactly 5,000 pounds as time stretches toward infinity? Well, mathematically, it's because that exponential term decays to 0. But physically, the tank is just reaching a steady-state equilibrium that perfectly matches the inflow concentration. 5 pounds per gallon in a 1,000-gallon tank equals exactly 5,000 pounds. The math perfectly, flawlessly predicts the physical reality. I love it.
Finally, let's look at Section 6, ODEs in broader engineering applications. As you push further into your graduate work, you'll start seeing how these foundational, separable ODEs are actually layered together into massive, complex systems. Just like we can couple two electrical circuits together in the lab, we can mathematically couple entire biological systems. For instance, the Lotka-Volterra equations take systems of differential equations to model unbelievably complex dynamics, balancing predator and prey variables to maintain sustainable fisheries in our oceans. It's wild to think about, but the exact same mathematical principles that figured out how fast our office building cooled down are out there literally saving entire ecosystems. So as you head out of this session and back into the lab, I really want to leave you with this final thought. Every physical phenomenon you observe, from a draining capacitor to a complex chemical reaction, can be decoded, modeled, and predicted if you simply stop and ask yourself, how is the rate of change behaving here? The math is just a language we use to describe the physical world around us. So how will you apply these foundational models to decode the complex systems in your own engineering laboratory? Thank you so much for your focus today, and I'll catch you all in the next explainer.
All right, welcome graduate students to this explainer. Now, as an electrical engineering professor, I basically spend my life looking at circuits and signals. But today, we're going to explore how a single, incredibly elegant mathematical modeling technique actually decodes our entire physical reality. Whether you're in advanced engineering mathematics or applied physics, mastering the ordinary differential equation, or ODE, is, well, it's basically a superpower. Okay, let's dive into this.
So think about this for a second. What could a cup of hot tea cooling on a desk, a massive industrial chemical mixing vat, and a skydiver in freefall possibly share? I mean, on the surface, absolutely nothing, right? They exist in completely different physical domains. We're talking thermodynamics, fluid dynamics, and classical mechanics. But beneath the surface, driving the physical laws of every single one of those systems, is the exact same mathematical engine. Today, we're going to learn exactly how to turn that chaotic reality into solvable equations. Let's talk about the art of engineering modeling. Because as engineers and applied scientists, our world isn't just numbers on a page. It's messy, physical stuff. Our real job starts by observing those chaotic physical variables and how they change over time. Ultimately, our primary job isn't actually computing the integral. It's setting up the correct model in the first place. The math? The math is just our tool to predict reality. Breaking that loop down into steps. Step 1, we observe reality and identify the variables. Step 2, we formulate the differential equation. And I promise you, this is arguably the hardest part, translating the actual physics into a mathematical rate of change, like identifying that a rate is proportional to a difference in temperatures. Step 3, we solve the equation using calculus. And finally, step 4, we interpret it physically. Because let's be honest, an equation is completely useless if you don't know what it means for your tank capacity or your resistor tolerances.
So, what is this primary mathematical tool we're using? It's the separable ODE, where y prime equals a function of x and y. The sheer brilliance of this algebraic manipulation is the isolation. We factor all the y dependencies over to one side with dy and all the x dependencies to the other side with dx. Once they're isolated like that, we just integrate them independently. It's elegant, it's clean, and it unlocks incredible predictive power.
But of course, there's a catch. When you integrate, as you all definitely remember from basic calculus, you generate that plus c, right? A constant of integration. And that generates an infinite family of general solutions. But in engineering, we don't build infinite possibilities. We build specific physical realities. That's exactly why we need an initial value problem, or IVP. By knowing the exact state of the system at time 0, like the exact starting temperature of our setup, we lock down that C and we find the one unique curve that actually models our specific reality.
To really appreciate the pure mathematics before we get bogged down in the physics, let's explore a classic initial value problem. Let's say we have y prime equals negative 2xy, with an initial condition of y of 0 equals 1.8. By separating the variables, just dividing by y and integrating those sides, we yield a very particular solution. Y equals 1.8 times e to the negative x squared. And what is that? It's the classic bell-shaped curve, a Gaussian distribution. In my field of electrical engineering, this exact curve is absolutely essential for modeling signal noise and probability.
Section 1. Thermodynamics, Newton's law of cooling.
Now, let's ground this abstraction in something you can touch and feel. Imagine an office building where the heating is abruptly shut off at 10 p.m. We want to know exactly how cold it's going to get overnight. Or picture measuring a scalding 161-degree cup of hot tea sitting in a room temperature 68-degree room. Honestly, who drinks tea that hot? But whether it's a massive glass building or a dangerously hot ceramic mug, the physical setup is literally identical. You have a hot object losing heat to a cooler ambient environment.
Here is where the separable ODE really shines. We formulate the model. The rate of temperature change, T prime, is directly proportional to the difference between the object's temperature and the ambient temperature. So we write that as T prime equals K times the quantity T minus TA. When we separate those variables, bringing the temperatures to the left and time over to the right and integrate, we get a natural log that exponentiates right into a beautiful exponential decay curve. By applying our initial temperatures, the math perfectly predicts that the building will drop exactly 9 degrees by 6 a.m.
Section 2. Fluid dynamics, industrial mixing problems.
Let's shift gears and examine an industrial mixing problem. Imagine a continuously stirred tank reactor. The physical reality looks like this. We have a massive 1,000-gallon vat. It initially holds 100 pounds of dissolved salt. Now, brine is continuously pumping in at 10 gallons per minute, and that brine contains 5 pounds of salt per gallon. Simultaneously, the well-mixed solution is draining out the bottom at that exact same rate of 10 gallons per minute. How on earth do we predict the exact amount of salt in that tank at any given minute?
Well, we use the universal principle of mass balance. Rate of change equals rate in minus rate out. Our rate in is a constant 50 pounds per minute, but our rate out? That depends on the current concentration, which is our variable y divided by 1,000 multiplied by the flow rate. This gives us our separable OD. Y prime equals 50 minus 0.01 y. When we separate and integrate this, the math basically hands us an exponential curve that perfectly predicts an asymptotic limit. Over time, the tank's concentration will mathematically cap out at a steady state of exactly 5,000 pounds of salt.
Section 3. Dynamics and decay, falling skydivers and isotopes.
Think back to that skydiver in free fall we mentioned earlier. The force of gravity pulls them down, but air resistance pushes back up, yielding a separable ODE for their acceleration. Now, I want you to compare that to a radioactive isotope. The Bateman equations tell us that the decay of a nuclide population is a probabilistic event, modeled by first-order kinetics, where the rate is proportional to the substance present. The physics involved, worlds apart, but they're separable differential equations. They are practically twins.
When we solved that radioactive decay equation, we hit a truly profound physical principle, the half-life. For any first-order process, the time it takes for half the substance to vanish is a constant. It's roughly equal to the natural log of 2, or 0.693, divided by the rate constant k. And here is the absolutely crucial point for you as engineers. This half-life is completely independent of the initial concentration. Whether you start with 1 gram or 1 metric ton of a radioactive isotope, it takes the exact same amount of time for half of it to decay.
Section 4. Synthesis. 1 Mathematics, Infinite Applications. When we pull back and synthesize everything we've just looked at, we uncover the structural mathematical DNA of the universe. Look at it. Radioactive decay relies on a rate proportional to the amount. Fluid mixing relies on rate in minus rate out. Newton's cooling relies on a rate proportional to a temperature delta. Yet they all boil down to integrating dy over y against a constant dt. And because of that shared DNA, every single one of these physical systems exhibits the exact same system behavior, exponential responses, whether it's decaying down to zero or asymptotically approaching a steady state. So whether it is fluid filling a tank, heat dissipating from a building, or a capacitor charging up in an RC circuit, the mathematics does not care. Separation of variables isn't just some clever trick you use to pass a calculus exam. It is the master tool we use to decode the inherent exponential nature of the universe. The math is totally indifferent to the physics. It just works.
This whole framework summarizes our entire journey today. We loop from identifying messy physical systems to carefully formulating the ODE, to applying our separation of variables to find the mathematical solution, and finally, looping right back out to physical interpretation. This right here is the true role of mathematical modeling and engineering. It is never about doing math in a vacuum, it's always about predicting reality.
I'm going to leave you all with this thought. You now possess the mathematical engine to model cooling rates, chemical mixtures, falling bodies, and atomic decay. If mathematics is indeed the true language of the universe, what other chaotic physical realities are out there waiting for you to decode with this single key? Start looking at the world through the lens of mathematical modeling, and I guarantee you'll never see engineering the same way again. Thanks for joining me on this explainer.